Okay, so the Clausius-Clapeyron equation. The relationship between vapor pressure and temperature is not a linear one. It's an exponential function. So the vapor pressure is equal to a beta, which is a constant. Yeah, that's a weird format. That's e to the power of negative delta H of vaporization over RT. So when we rearrange that, we get this, and then you can graph it. And so you graph natural log of the vapor pressure versus 1 over the temperature, and that gives you a straight line where this is the slope and that's the intercept. So you get a line like that. Scientists do this a lot. They'll take this observed relationship and they'll do stuff to it. They'll take the log of it, or they'll mess around with it, because if you can get it to be linear in some form, you can predict things so much better, and you can have a nice equation for it, and it's just so much more useful. So that's what we do a lot. So there's an example of how that's done. And in the lab we did with the comparing atoms and oranges, you graphed a ratio of diameters against packing efficiency, and that gave you a straight line, which helps you to predict the maximum packing efficiency. Or you're going to do that later today and turn it in tomorrow, right? Okay, we'll look at that. So, just backing up here just a minute. So the slope here is the heat of vaporization divided by R. And so we can calculate this or determine this experimentally by graphing and measuring and then graphing, oh my goodness, vapor pressure at different temperatures, graphing the data, and then from the slope we can come up with the heat of vaporization for that particular liquid. So that's how they come up with those things. So as an example, the vapor pressure of carbon tetrachloride was measured as a function of the temperature, and the following results were obtained. Determine the heat of vaporization of carbon tetrachloride. And we're given temperature in Kelvin and vapor pressure in torr. What's the next slide? That guy. Okay. So what we would have to do is graph this data and determine the line. So we would find, right here, we would find the natural logarithm of the pressure and 1 over T in kelvins. So there's the temperature. We'd have to convert that to 1 over Kelvin, and we'd have to take the natural log of this and then graph that, actually. And I don't know about you, but I don't really feel like doing that on the board right now. That's what computers are for, right? And that's not, asking you to graph something like this is not something that will happen on an exam, right? Because they don't give you graph paper. We're not going to do that to you. You'd find the slope. The slope is the negative delta H over the gas constant. So I don't know even why I put that one in there. We can also express the Clausius-Clapeyron equation in a 2-point form. And this is useful to predict the vapor pressure at a given temperature from the heat of vaporization and the boiling point. And so basically what we're doing is we're taking that equation and we're putting 2 points. So there's a pressure 1 and a temperature 1, there's pressure 2 and temperature 2. And these would be on that graph. So in this way, if you know the boiling point, say, What is the vapor pressure at the boiling point? It's equal to the external pressure, the atmospheric pressure. So at a liquid's boiling point, its vapor pressure is going to be 760 millimeters of mercury. And then if you know the heat of vaporization, you can calculate the vapor pressure at the other temperature. So we'll do that one instead. So let me refresh my memory. P1 over P2. Gosh, I could just copy that. P1 over P2 and T2 minus T1. Let's see if I can do that. So the natural log of P2 over P1 is equal to negative delta H, the heat of vaporization, over R times 1 over 2, T2, minus 2, thank you, T1. They say there's 3 things that happen when you get older. One is you lose your memory, and I can't remember what the other 2 things are. So here's our problem. Propane has a normal boiling point of minus 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What is the vapor pressure of propane at 25 degrees Celsius? So we can identify either of these, minus 42 or 25, as T1 or T2. We can call them whatever we want. I'm thinking that if we're solving for P2, that might be logistically easier. And so let's call our, we'll call this one T2. And this one, yeah, I don't know how that works. I say 2 and I write 1. Just, we're going to call that one T2. We're going to call the other one T1. Blue on blue is real easy to see that. And here's our heat of vaporization. We need pressure 1. The pressure at the normal boiling point. What is the pressure at a normal boiling point? 760 millimeters of mercury, or 1 atmosphere. Okay. Does it matter? Well, yeah, actually it does, because of R. R is in there, and so we need to use whatever pressure units are appropriate for the R that we're going to use. Okay, the one that we have memorized is 0.08206 liter atmospheres per mole Kelvin. But then we look at this heat of vaporization with the 19.04 kilojoules, and that doesn't look like that's going to work out very well, does it? So then there are other values for R using different units. So I'm looking that up right now. The gas constant is also 8.314 joules per mole Kelvin. And that sounds like that would work out with our units a little better. So 8.314 joules per mole Kelvin.
So then it doesn't matter what you use.
Yes, that is correct. I see that now. Could we start today over, maybe? No, you don't want to take that exam again. We always have to be concerned about units on R, but the pressure units actually don't end up mattering because it's a ratio. Which just, I don't know, completely missed that. So whatever unit you start with is what you end up with. So we can use torr, millimeters of mercury, atmospheres. Let's use atmosphere because it's a nice number, because then we'll be dividing by 1 and that'll be easy. I'm up for easy. We need these temperatures in Celsius or in Kelvin? Kelvins, okay. So, bless you. So T1 is minus 42 Kelvin. So we've got 273 minus 42, 231. And T2 is 25 degrees Celsius, which is 298 Kelvin. That one gets used a lot. So now we're going to have the log, natural log, of P2 over 1 is going to be equal to the negative heat of vaporization, so 19.04. My stylus is having a fit. This isn't going to fit at all. Start over. I'm going to start down on the bottom. So the natural log of P2 divided by 1 is going to be equal to 19.04. And look at the units there, kilojoules per mole. The units that we have on R are joules. So instead of kilojoules, let's just write in what kilo means, which is 10 to the third. Joules per mole divided by 8.314 joules per mole Kelvin. And then we've got 1 over T2, 1 over 298 Kelvin, minus 1 over 231 Kelvin. So depending on how your calculator thinks, you'll do this in different ways. But I'm going to take 1 divided by 298 minus 1 divided by 231 and press the equal sign so it finishes all that. I get 0.0009733. Then I'm going to multiply by 19.04 times 10 to the third. That's a negative. And I'm going to divide by 8.314. And I'm going to get that the log of P, natural log, is 2.2289. So, just start that over. 2.2289662 is what my calculator is telling me. I would really advise against rounding that. And then you need to take the anti-natural log of that, which is e to the x. So it'll be e to the 2.22 blah, blah, blah. And I get 9.29. Let's see, 4, I think, yeah, the sig figs get really kind of messy here. So P2 is going to be 9.2903 atmospheres. And what is wrong with that? Is that a reasonable result? No, it isn't. Because something boils at 1 atmosphere. So we're expecting this to be less than an atmosphere. So I'm thinking, maybe I did something wrong with my calculator. T2, T1.
1 over x probably?
Well, I shouldn't need the way I did it, I didn't use 1 over x. But we're solving for P2, not 1 over P2. Let me try it again. And someone's calling me. This is fabulous. Divided by 8.3. Yeah, I'm coming up with the same result. Pause. Okay, so we did the problem correctly. It was my thought process of the reasonableness of this answer that is off. Propane boils at minus 42. So at 25, its vapor pressure is going to be above 1 atmosphere. So the 9 atmospheres is okay. I think we're all a little weirded out, aren't we?
How do you get the 9 again? You go from the 2 point.
From here to there, the natural log of P2 is equal to this.
Right.
So then P2 equals E to the 2.2289662 business. So we've used log and anti-log buttons on our calculator. This button is near that one, but instead of log, it's ln. It's the natural log. It's got a base of E, which is an irrational number, I believe. No, not irrational. It's like pi. It just goes on and on and on. Yeah, I think it is rational. Irrational is when you've got like this square root of -1 kind of thing going on. Those math terms, you know, it's like I know how to do stuff, but I don't know what it's called anymore. But what's more important? Knowing how to do it or knowing what it's called? It's more important to know how to do it. Anyway, so now that that was a big fiasco, any questions about that problem? No? Okay. The critical point. What happens if we vaporize a liquid in a sealed container with heating? So we put think of putting water into this like thick metal container and you heat it up. It's going to get hotter, and as it warms up, the pressure in there is going to become greater because the vapor pressure of the liquid becomes greater and more of it gets into the gas state. And then it vaporizes, and we've got a gas in there and the pressure's rising, and as we continue to heat it, the gas becomes more dense and the liquid becomes less dense, and finally at a certain point the gas and the liquid states actually merge and they become a supercritical fluid. And so this is actual photograph of this happening in a container. So you've got the liquid and you've got the gas, and as you increase the temperature, the liquid becomes less dense the gas becomes more dense because of the pressure. It's being squished together. And they begin to sort of merge, and eventually you get a supercritical fluid where there is just one state. It's not a liquid or a gas. It's kind of both and none between them. And the temperature at which that happens is the critical point. So Tc is for the critical point temperature. Critical temperature is the temperature at which a supercritical fluid forms. The liquid cannot exist above that particular temperature. And the pressure at which that happens is called the supercritical pressure. Supercritical fluids are great for solvents. They're awesome. So they use supercritical CO2 to decaffeinate coffee. And so they can get the caffeine out of the coffee without leaving any residues behind. Because when you're done extracting the caffeine out of it and you bring the coffee beans back out of the chamber, what happens to any residual CO2? It floats away. CO2 is in the air anyway. Adding a little more is really not an issue. We do it all the time when we breathe. And so here we have this fluid that's going to be non-toxic and not leave any residue, but we can use it to extract the caffeine. Of course, that begs the question, why would you want to do that to coffee? Because isn't that the only reason to drink coffee? I'm not a coffee drinker, but I am a fan of caffeine.